Hey everybody, and welcome to another episode of EEs Talk Tech. As always, my name is Mike Hoffman.
I'm Daniel Bogdanoff, and today we have Kenny Johnson. You've probably seen Kenny on our YouTube channel before. He came around during Scope Month, gave us a great little tip about how to use like a $10,000 active probe to clean out the charging port of your iPhone.
That's right. That's right. I forgot about that helpful tip.
Still, to date, my favorite Scope Month video with Kenny, Dr. Kenny, and his Dr. Science glasses. Today we're going to talk about power integrity because Kenny is our resident power expert. So, Kenny, can you introduce yourself a little bit? Tell us about your background. And
yeah, sure. You know, but before I go too far, though, expert is a loose term. It's like calling me a giant, even though I'm just the tallest pygmy in the tribe, right? It's expert relative.
We've had on this podcast says, well, you know, expert. So I've come to convince myself that experts never think they're experts. So
yeah. Okay.
Carry on. Sorry.
Yeah. So, you know, I've been working for this place for like 32 years now, and most of that was in R&D. And but I've taken a couple of trips over into marketing as like product line manager and stuff like that. And best part about the job has been through all those years just visiting with hundreds or maybe 1,000 different users out there and helping them solve their problems. And you know, my expertise really is more about like probing and making good measurements. And it's turned out the last maybe 3 or 4 years when I've been working on this stuff that people have just really been having a hard time with what I call the power consumer. There's people out there that produce the power, and then there's the people that use the power. The people that produce the power, you know, they're the ones that, you know, whether that might be the wind farm or the solar farm or just the coal-fired power plant, all the way up to the plug in the wall, and even from the plug in the wall up to kind of like the, you know, the silver can that's your AC to DC power supply inside your whatever product you've got.
Sure.
That's kind of the power producer. The power consumer guy is the guy that's taken that, and he's worried about the quality and quantity of the power that he's using. And so I really started kind of get into this, like I said, I don't know, 4 or 5 years ago or thereabouts, and people were sweating like chasing the milliamps and the microamps and stuff like this around, and so we were helping them make those measurements, and then people kept raising their hand asking like, hey, you got something that can look at the ripple noise on supplies? And I don't know if as a kid your folks ever read you the book Horton Hears a Who, or you saw this story, right? But you know, at some point it's like all these little people are screaming for help, and then just one more voice gets on there, and then it finally registers. It's like,
it's this little dust speck that the elephant is protecting, and then like no one can hear it except for him because he has giant ears.
Yeah.
And then there's like one like teenage kid who's like, I'm not gonna yell, whatever. And he
exactly.
does. And,
and so finally
like,
there's some threshold of voices where I finally heard I was like, oh my gosh, we need to do something for these folks. And so that's when we started making like power rail probes and things like that, you know, to help out with this power integrity. So it's so for the power integrity, it's you know, the rough definition is something almost esoteric sounding, like the study of the effectiveness of the conversion and delivery of DC power from the source to the gates on the IC.
I'm on the edge of my seat right now.
Yeah.
Are you reading out of one of your textbooks here? Please tell me you wrote one of these so you can say you wrote the book on it, or?
Yeah, no. I loosely quoted that, so I don't have to actually name my source.
That's fine.
But really, you know, folks they were freaking out about like, hey, I need to measure the ripple and noise on my supplies. And we didn't really have a good solution for that. So then started digging in more and more and found out how much all this stuff is tied together, that what's happened over the years, you guys are all familiar with Moore's Law, right? That every 18 to 24 months, we're going to double the number of gates on an IC.
Sure.
Yeah, interesting thing about that, I read a guy's paper where he says, you know, if Moore's Law keeps up for about the next 600 years, we will have a computer that is capable of simulating every atom in the known universe.
Ooh, Hitchhiker's Guide to the Galaxy style.
That
right?
Are we living in a simulation?
Yes.
Is that what we're going to talk about? That
that's exactly where that article went. But anyway,
and to have a backup, right? That's the Hitchhiker's Guide is like at the end of the series, they're like, oh yeah, here's the backup, and then everything like resumes as if it were real life again.
Anyway, so with that, what happens is, you know, we've been cramming more and more stuff in there, and so you start getting more and more gates packed together on everything, and we start ending up with like thermal hotspots. You know, just too much power. You know, you're gonna fry devices and everything, and so to take care of the power for those hotspots, but also to extend battery life, or just you know, how many kilowatts your thing is using out of the wall. is we start dropping voltages. And so everybody starts getting more and more concerned about this ripple and noise on the supplies and supplying good, clean power to everything. And so that's where we all started. And, it's there's actually, when I first got into it, I went out to Amazon and I said, okay, I need to read a book, right? Mm-hmm. And so I started checking some books. And all the books that were published, I think there was 2 at the time, maybe 3. I mean, they literally were just coming out about 3-4 years ago. So it's been something that is really exploding for a long time. Now, the truth be told is that people have been doing power integrity measurements. The first reference I ever saw was from some work in like 1930. So people have been like looking at this. It's just that right now it's become more and more important because if product functional reliability is directly proportional to the quality of the power inside that product. And so as we have a lot more functionality in our products, whether that's your smartphone or my cool little, exercise wristband kind of thing, there's more and more opportunities for things to go south and to fail. And so that's why there's this increased focus on this. And there's a correlation then, or they're kind of tied together. Well, we're supplying a voltage to these things that they're operating, and they're also consuming current. They're pulling current through there. Okay. And so you start thinking about this, it's like, wow, so that's sounding vaguely familiar to like Ohm's law, right? And we're just missing like the R. Where's the R in the whole thing? Well,
right, or the Z.
Yeah, exactly. And so if you think about it, like a typical product is going to have power and ground planes. And you're going to want the impedance of those things to be pretty low so you're not getting some kind of IR drop across the ground plane. And so I know it's a gross simplification, but it's a pretty easy model to work with, is that the idea coming from some of the early pioneers of this stuff, Istvan Novak or Ray Ridley, guys like that, they talk about these flat impedance power planes. And the idea is you kind of take whatever your voltage is, if it's a 5-volt supply or whatever, divide it by the change in current that you expect. What's basically your peak current? Multiply that by the tolerance, and you end up with like a target impedance for your power planes. Huh. And so if you can, maintain pretty much a flat impedance, what happens then is you don't get a whole lot of noise showing up on your power supplies. So if you think about it, it goes something like...
You want a flat impedance over the different current ranges, right?
Over frequency.
Over frequency ranges.
Yeah.
Okay.
Yeah. And so, if you think about it, remember back to Circuits 101 is that an inductor is open at high frequency. And so we've got these power planes, and really those are just big inductors. So at some point, their impedance is going to go up. And so when you have things like you're just writing data out to memory, well, there's some pretty fast transients there. They're associated with 0, 1, 0, 1. It actually takes some energy to change that from a 0 to a 1, and you have to draw some current to do that. When you do that, the supply kind of pulls down and sags. And anyways, so the point is there's, even though we're talking about DC, is that there is high frequency effects here. And so that's why it's impedance, not resistance to those planes. And so when you look at boards, a lot of the times you'll see like how there's all these like capacitors all over the place, right?
Yeah.
And the job of the capacitor, remember back again that same circuits class, a capacitor is a short at high frequency. Well, kind of picture it in your head as you start going from like, DC on out, that impedance of that inductor is starting to creep up. Well, that's bad. We want it to go back down. What do? Hey, let's slap a capacitor on it because that's a short. That'll start pulling that impedance back down. But then at some point, there's some inductance associated with that capacitance, and it's going to start to go back up again.
Sure.
And so when you look at these power plane impedances, they just look like kind of like waves on an ocean. It's just kind of these troughs and peaks and everything that are the impedance. And so that's what guys are like trying to design towards, whether they know it or not.
So basically, like to sum that up, when a system requires current, it's basically going to be a load pulling current, and the supply is going to dip a little bit. Mm-hmm. And if it's, for example, writing 1010, it's going to pull and release. Yep. Current, power supply is going to ripple.
Yep. That's it. That's it exactly. And so with a lot of products like maybe the ones that we design here and everything, we've got fairly good sized circuit boards inside our scopes, many, many layers, robust power planes, robust ground planes, things like that. But if you think about somebody that's doing some small form factor product like maybe some IoT thing or consumer electronics or even smartphone kind of thing, they probably don't have room for dedicated power planes and ground planes. Heck, a lot of stuff I take apart to fix at home only has it's only a two-sided board, so they have like a power trace and a ground trace.
Yeah.
Well, that means that they're going to be fighting that impedance battle pretty quick. And but where most people come into this is they, at least from what I've observed, is the majority of people try to use some intuition and based on past experience to go through and make the planes kind of as big as possible and keep distances as short as possible. And that's why you see the trend of more and more like localized power regulation. Maybe in the past it used to be you just have one fat hose that goes to your circuit board supplying the power and you just distribute it everywhere. Well, now there's more and more localized regulation, so you can keep those distances shorter. The other thing that it does, too, is it was mind-boggling when I first got into this was, for example, like a typical solid-state drive has about 12 supplies in it. Something like a tablet could have 50. Some of our oscilloscopes have 180 supplies in it. And some next-generation mobile electronics, 100 to 200. Now, it's not like there's 100 different voltages, 1.1, 1.11, 1.12. No. There's redundant voltages in there because what happens is if they're all connected to the same spot, as I turn on the display, it's going to yank a bunch of power out of there or a bunch of current. The supply is going to sag and it's going to
affect everything. Yeah.
Yeah. And it's kind of like when I was in college, we rented a really old house, and if I was in the shower and somebody flushed the toilet, all the cold water goes down the toilet and I get scorched. It's like, right? So they put in some flow regulators and all that. Well, these are doing the same thing so that when somebody turns on the display, it doesn't disrupt the the MP3 codec or the memory or something else. So that's why there's these multiple copies. And then they also try to have multiple phases so that they're, again, even more robust for when there's when there's these demands on these voltage regulators. Anyways,
wait, so they're going to run three-phase power across the board and rectify it out at different voltage levels?
Oh yeah, no, I didn't mean it that way. What I meant is there may be let's say there's a 1.5 volt supply to something. There actually may be multiple 1.5 volt DC to DC converters there and everything that are sharing the load so that they can
having two regulators attached to the same rail. If one gets hit, the other one is able to stabilize it.
Yeah,
okay, that makes sense.
And so sort of like two or three of us carrying the load instead of one of us carrying the load.
I was like, that's going to be brand new to me. We're going to have to pause for a moment there.
Yeah, right. Wow, what do those connectors look like? Man, how do they do that?
How did I miss that technology?
Is that in my phone? No,
your phone's converting DC to AC and then rectifying it again somewhere else.
Yeah. And
that's efficient.
Yeah, so let's see, where was I going with that? Anyway, so you've got all these supplies you got to look at. And so most people, they're just using kind of an intuitive approach to this. And it's because a lot of folks don't have access to maybe modeling and simulation tools. And I know around here, we've got some modeling and simulation tools, but we're a large enough corporation that we've got people that are dedicated to support those tools and be experts on them. But, a lot of people aren't that fortunate. So they just kind of have to take some rules of thumb and just say, well, I'm just going to make this, throw down a lot of copper and start sprinkling a lot of...
just over-engineer it a little bit.
Yeah, exactly.
Adds cost.
And so how do they know if they did a good job or not? Well, you go look at the data sheet for the FPGA or the little microcontroller, and it'll tell you on these critical supplies, the maximum, ripple and noise and fuzz on the power supply is, plus or minus 2% or 5% or whatever it is. And so they want to go measure that to see if they've done their job or not. And so that's where most people jump in. And then excuse me, after they've gone through that a bit, then they start to kind of maybe think a little bit more about next time when they lay it out. Maybe they'll go take a class or maybe read some of these books. But in general, it seems like that's where most people hang out, as they sit there in that in that world, kind of measuring it after the fact, and not necessarily looking at it in the impedance domain, but more in the time domain when they're measuring that stuff.
Interesting.
Now, I do have to ask, you brought some show and tell items. For those of us who are listening and not watching, you have a couple of, looks like 4 textbooks and some printouts here that you brought in. Was that just in case we tried to stump you or something like that, or is there some stuff in there you'd like to share?
Well, this is so that I can try to pretend I'm cleverly disguised as a power expert, and so this is part of the disguise is having a stack of textbooks that's about 8 inches tall.
Before you start believing Kenny's claims, I think I've come to a conclusion: is one, that experts are always learning. So if you want to be an expert, you have to keep learning. But I think you also might hold the record for most patents in the company. Is that, I don't know if that's an official record. Do you know how many patents you have?
So, it's
a lot.
Quick, cute story on that. So, our chief technology officer used to have the most patents for this particular division, this location here.
And Jay Alexander. Yeah.
Yeah, in Colorado
Jay,
Springs.
if you're watching, hi Jay.
And
he watches our channel sometimes.
Oh, does he?
Nice.
Cool.
Yeah,
Hey, Jay.
Hey, bud.
And
now he has to watch.
So Jay congratulated me a while back. I think because my boss had sent an email to some folks saying, hey, Kenny got a patent. And so Jay had asked me how many, and I said, I try to remain humble on that. I'm not naturally a humble guy.
You don't brag about it. That's why I had to bring it up. But
yeah. And so I think the current count is almost 30.
Jeez.
And when Jay and I were having the conversation, I think his number was about 25, and I just got number 26 or 27. And but hey, I've been turning the crank for a long time, so that's. But there's guys out there, I think, at the company, like within Keysight, that have over 100, over 200. So.
TLO guys, I'd have to assume.
Oh yeah,
Cutting edge
like
stuff.
The technology leadership, ASIC guys like Mike Byers and some of the other guests we've had on the show.
So there's definitely some intellectual giants out there.
Okay.
But anyways, with the books, the reason I brought the books was because they actually helped me out a lot. Like I said, when I first got into this, I was a probe designer, not some kind of like power engineer and everything. So how am I going to help these guys? I had to come up to speed fast. And so I hit Amazon and was checking out power integrity and start finding like one book was published, then 2, then 3. And so I order them and just kind of read through them and everything. And for those that are listening, there's no point in me kind of holding them all up and everything, but there's at least 3 or 4 great resources out there. If you just go hit Amazon and type in power integrity, you'll see.
Is there one in particular that you'd choose? Like if you had to recommend? And it's not an official endorsement.
Yeah. If you don't have much time to read at all, there's a book by Dr. Eric Bogatin, and his original book was called Signal.
Sorry.
Your long lost cousin.
Yeah. He originally wrote a book called Signal Integrity, and then he did an update to it that was called Signal Integrity and Power Integrity Simplified.
Okay.
And so that's the second edition of his book. And so there's about 2 or 3 chapters in there, and it's a pretty good overview. I think he's got another edition out now that's got even more content. But if you just want to start there, it gives you some great ideas about, like, why should I even care? What happens? I mean, as long as it's there, we're good. And so he tells you why you should care, some steps to take, some measurements to make, and that's a good basic one to start with. And something that I wanted to share, just this quick experience, was as we were going around and starting to talk to people about some of the techniques and things that we had for measuring the ripple and noise on the supplies. I remember talking to it's one of the first users. They were in a lab that they called their SIPI lab. So this is a very large, like Fortune
Signal integrity,
100.
Power integrity?
Exactly. And
not like sippy cups. 'Cause my house is full of those right now.
Yeah, and little Cheerios glued everywhere. Right?
Get ready to double it.
Yeah.
Yeah, no kidding.
Anyways, and so that's the thing, is they're so tightly related, is that power integrity will affect your signal integrity. Power integrity also affects your EMI and your EMC. But anyway, so these guys at a lot of the more progressive or in the forefront companies and everything have these SIPI labs and everything. So I went in there and I was talking to the manager of the power integrity part, and we're showing him how to make some measurements, and he's like, "Wow, that's great results. That's better than I could get before," and everything. And he says, "You know what? I wish there was a button I could push that would tell me, is it worth improving the design anymore? Because he says, like as engineers, we can always like diddle it and tweak it and try to improve it, but is it worth it? What am I going to get from this and everything? And so I think there's, without getting into endorsing particular products, there are some more tools out there now, be it analysis applications or even some of these textbooks that can kind of help you understand then what you can get. Because get this, there's multiple papers that say power supply induced jitter is the single biggest source of data jitter in a digital system.
Interesting.
And I've got a couple.
Believe it.
Yeah, I've got a couple of cool little IoT development kits. So if I was like wanting to make my little fish tank monitor for at home or whatever. Well, anyways, I take these and I can, without even trying, they start stumbling and dropping bits, which would be basically, okay, that's either going to affect my battery life because, I didn't, my error checking says, okay, send me the data again, send me the data again, send me the data again, or maybe it's actually things freeze up. And so that power supply induced jitter is really kind of the thing that people are looking at. And so there's some papers out there. We've got some, but basically if you go check that out, if you clean up your supplies, you're going to get a lot more margin in that domain.
So to clean up a supply, is it like a bypass capacitor thing you have to go through, or what does that look like?
Wire brush.
Yeah, soft bristle toothbrush.
Yeah, that's actually the majority of the time. That's really what it is. Is that like when remember when I was talking about that flat impedance profile? Well, let's say you've got some noise that's showing up in your system. That's we instruct people, like after you've looked at the power supply in the time domain, good thing to do is go look at it in the frequency domain. Throw up an FFT. And then you'll start seeing some spikes in there at the various frequencies. And that's usually a good way to kind of get a fingerprint or, tell some DNA for like who's committing the crime. You're like, okay, I see a 100 megahertz spike or whatever. And so then, okay, so that's starting to bleed through. Now I need to do something to try to suppress that 100 megahertz noise from my supply.
And if you know the frequency, you can work backwards into the impedance that you need to help.
Exactly.
Counteract
exactly.
Okay.
So if you were to go look at that impedance profile, you'll probably see that your impedance is starting to pick up around that 100 megahertz. It's like, okay, let's go pick a cap that's going to knock that down about there and go plop that down and everything. And that's kind of, at the easiest, that's what most people do.
Okay.
And
you want to put that, if I remember right, I was just learning more about this. You want to put it like right by your load.
Yeah.
You don't want to put it out by your power, like at the source of your power rail. You want to put it right where the chip is going to need it or whatever your load is.
Yeah. It seems like there's some general rules in the universe that apply to just about everything. And like closer to the device is always better. Whether you're like putting down the bypass caps or like we're always telling people, like if you're making a measurement, where are you going to go measure the signal? Well, you want to go measure it at the receiver, right? See what the receiver's seeing. And because that's going to tell you a lot more. So those general ideas of like closer to the device that's being powered or closer to the device that you're concerned about. And so yeah, you go through those there. There's one thing that
so I think before you get into wide bandgap,
Yeah.
it's been like 24 minutes
No.
or so. So I told you it goes quick. So we might have a whole nother podcast on wide bandgap
that's cool.
power.
That's
Because
cool.
I think that'd be pretty cool too.
There's
Like you want to tease it, like gallium arsenide and super fast switching?
I'll just throw this out real quick. This is from the U.S. Department of Energy. I was looking at this just a little while ago, and they'll actually pay for guys like you and me to go back and get a degree in power engineering. And the reason is because these wide band gap semiconductors, gallium nitride, silicon carbide, if, for example, we were to just go through and change the existing motor controllers out there for like pumps and things like that, we could save enough electricity for 1 million homes. It's just because they're so much more efficient. If we change
How many homes are in the U.S.? It's like
I've wondered
Average
that.
home size is like 2-ish, so
And
it's
the
got to be
population's-
could be a couple hundred million.
population's what, 700 million?
About
350.
300. Oh, I'm way up.
350 million.
Okay.
Yeah.
Samsonite.
And so I was looking at this, and if
So
we just
all the homes.
so if we went through and changed just like existing like your wall warts and the motor controllers and stuff like that, it's about maybe 5-6% of the homes in the U.S. right? Just from changing those out. Anyways, it's the wave of the
Interesting.
future for
Okay.
power electronics.
Perfect. So we're going to talk about that next episode. Real quick on the census data. there was just a really interesting research study out. This is totally unrelated, but I have to share it because it's so cool.
Nice.
So, you know, like Facebook advertising says, oh, I can reach this many people in this age gap. If you look at what the social media sites say they can reach from advertising standpoint and what the U.S. Census data says, Facebook is claiming, and these other advertising tech companies are claiming to reach like 40% more people than the U.S. says actually exist in the country.
I believe that.
So I don't want to dwell on that, but I just had to point that out.
Yeah,
Sort of this weekend, like, oh, okay. And I probably believe Facebook over. It's got to be somewhere in the middle because I'm not going to go there anyway.
Yeah. I'm with your sides.
So at the end of every podcast episode, we like to ask our guest a stupid question. So I think I know what your question is, but go for it.
No. Yeah,
okay. Well, I'm going to ask it for you because this is what you'd come up with.
Okay. All right, you go first. Then you go.
What
first.
is your favorite power rail voltage and why?
I didn't even think of that.
Wow. I'd have to say 3.3.
Okay.
I love the symmetry of that number.
It's a good number.
It's a very complete number.
I remember when 3.3 was the small stuff. Everything was 5 volts when I first started working, and it's like, oh, you're working with the small stuff, 3.3. But it's just the symmetry of that 3.3. Yeah, that's definitely my favorite.
It's nice.
Did you have a question too?
I do.
Okay.
So
I like 5 volts because of USB. Go ahead. Makes everything easy.
So we've been talking a lot about power integrity, so it sounds like that's getting a lot of attention. What other part of electronics designs do you feel like deserves more integrity? Doesn't have enough integrity. What do you think?
Yeah. Who doesn't have enough integrity? No,
Don't use names.
Data security. What do you think?
Those quantum computing guys.
Unfortunately, my wife's car got broken into yesterday, and her purse got stolen. We had to freeze all the credit cards, and so that brings a certain.
It's probably good to do anyway after what happened a few weeks ago.
Well, that's what I'm saying. So actually, the blessing in disguise here is we're getting new credit cards issued across the board, and I thought about that last night, trying to make lemonade out of lemons. Was going, well, hey, okay, so somebody hijacked all my stuff from that one credit bureau.
Right.
Some of that information is bogus now. Where people are struggling right now, that the other thing with integrity is just counting the milliamps that go everywhere. People are trying to save power, whether it's to be green to save the planet or be green to save some green. And so that's the other phase of this that where I think we're starting to see a takeoff is just how many coulombs am I scooping up and throwing away and everything? How much current am I using?
It's being distributed cleanly, but is it being used effectively? Is that what you're getting at?
Yeah, exactly. So, whether we're trying to save the planet or, I did a thing like about 10 years ago, got an infrared camera, and for work. Well, what's the first thing you do? Well, hell, you take that.
Take
home.
a selfie.
You got to go home.
Right.
You got to go home and check stuff out, right? And it's like
Windows
show the kids
and
so checking out the dog, and it's like, whoa, he's well insulated. Only his nose glows and his ears or something like that. And then we're like doing handprints on the wall. But as I moved around the house, the number of things that were glowing that I thought were off, Go down to the basement. Wow, look at the treadmill. Oh, look at the furnace, the thermostat, and just how much of that is wasted. And so whether you're green for that or just being green to save the utility bill, is that I think that's the other push is just using it more efficiently.
Soft power switches are cheaper. I think that's what it comes down to.
Yeah, could be.
Yeah.
We all have our favorite YouTuber who's very, 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 very fond of actual physical power switches.
Yes, we do. Yeah.
Give him a shout out, Dave Jones.
Yeah. And Electro Boom actually did a great video with a thermal camera he ran around. It was pretty funny. So you can go check that out. All right. So we are officially out of time. So thanks for tuning in. Make sure you subscribe to the podcast. Give us a 5-star rating, please. That really helps us keep doing what we're doing. You can also see this podcast in its entirety and get the RSS feed and all that type of stuff if you do custom feeds on EEsTalkTech.com, EEsTalkTech.com. I'm Daniel Bogdanoff. Mike Hoffman and patent heavy Kenny Johnson is with us, and we'll have him back next time to talk about wide band gap semiconductor power or something. I don't know. We'll figure it out next episode. Thanks for watching. See you next time.
Cheers.
Adios, guys.